Okay, good morning everyone. Oh, sorry, I should turn this on. Good morning again. Can you hear me? Yes. Okay, so this is going to be the last lecture, and the plan for this lecture is to finish, so we're going to keep talking about supersymmetric QCD, and the things that we're going to see, we're going to finish the F smaller than n example that we did. Then we're going to skip to F equals n plus 1. And it's not because the F equals n is not interesting, it's just because of lack of time. And in principle, you could go back and recover that on your own. And finally, we're going to move to F above n plus 2, at n plus 2 and above. And there we're going to see Seiberg duality. So that's the plan for this last lecture. Okay, so remember what we did yesterday. Yesterday we started talking about F smaller than n, and we derived the superpotential based on symmetries. We used the various global symmetries that we had, and we derived the superpotential that took this form. It was the determinant of m, and this was to the power 1 over n minus f. Now, this was derived very long ago by Affleck, Dine, and Seiberg. So it goes by the name of the ADS superpotential with a capital D. And the first thing I want to do is I want to show another way of deriving the same thing, just so we see another way of doing that. So the thing that appears up here is this lambda to the b. And remember that yesterday we talked a little bit about spurions and how we can use spurions to derive all sorts of constraints on the superpotential. So you could ask yourself, can we think about this guy as a spurion? So if it's a spurion, it's some sort of background field, and it should violate some symmetry. So then the question is, which symmetry does this violate? And remember that we started talking about anomalies a little bit yesterday, and we said that the U1A symmetry, the axial symmetry, was anomalous. Now, there are a number of ways to look at this, but you could say, what happens under the U1A symmetry? Under the U1A symmetry, I have Q's and Q bars here. There's F of them. Each one of them has charge 1. This is charge 1. This is charge 1. So altogether, they contribute 2 F units to the U1A anomaly. I could also look at the instanton generated amplitude, which has one external leg for each one of the fermion zero modes. So in particular, I have Q1, Q2, and so on. All these guys appear here, and so the whole thing carries charge 2F under U1A. This thing is proportional to E to this power, which is precisely lambda b. So we can associate a charge of 2F to lambda b. So now we can say, okay, this can be regarded as a spurion for the axial symmetry, and then if we use that, then let's derive the superpotential again this way. So we start again with the SUF times SUF symmetry that tells us that the only thing that can appear is the determinant of n. Then we look at the R symmetry. So that tells us that we should have det m to the power 1 over n minus 1 over n minus f. And finally, we look at U1 axial, and under U1 axial, that M has charge 2f, because remember, this is basically QQ bar, the determinant of QQ bar, so you have each one of the Q's and each one of the Q bars appear once, so this carries charge 2f, so that means that what we should really have is a combination of lambda to the 3n minus f over that M in the superpotential. And because we already have this from the U1R, we conclude that W should be the thing that we got before. So we recovered the same thing that we had before, and notice that in this case we didn't have to use the dimension of the superpotential. The thing I did before, at the very last stage, I had to say the superpotential has dimension 3, and that's the thing that fixed the power of lambda here. Now you can check that, obviously, this has the correct dimensionality. This has dimension 3. So that's another way to derive the same thing. Now, you can think, okay, very well, so, we have to understand what this means. This means that if there is a superpotential, this is the form of the superpotential, and it's exact. There's not going to be any correction. We derive the full superpotential. Of course, we don't know that this thing is actually there. And if it's there, we want to understand where it's coming from. What's the physical source of this thing? So let's think about this a little bit. The first thing to note, and we'll come back to this very soon, is that obviously there's not going to be any minimum at the origin. What this thing wants to do is to push you away from the origin. So let's look at some expectation value of the Mazon matrix. And just for simplicity, remember this is an F by F matrix. Just for simplicity, let me take it to be the identity. Okay, so I want to turn on equal vivs for everything. If I want to be a little more careful, I should really put V squared here, because this is a QQ bar. The Mazon is QQ bar. So now let me look at what's happening along this direction. So along this direction, all the quarks are getting vivs. In other words, it's essentially this thing. There's F of these guys and n minus F rows here. So our SUF gauge theory is broken, our SUN gauge theory is broken to SU n minus F. Now, what's the scale of this? So first of all, what do we have? We started from this SUN theory, we went along this flat direction. We have an SUN minus F theory that's completely pure Yang-Mills. There's no more light flavors that remain. So this is just pure SUN minus F. What is the scale of this theory? So lambda L to the power 3 n minus F, because that's just the beta function with no flavors, that should be equal to, we should match the couplings basically at the scale V. So up here we had our original SUN theory with F flavors, then at the scale V, or actually physically at the scale GV, all the gauge bosons got mass. But with our funny normalization, we can forget about the G. And down here we have the SUN minus F theory with no flavors. So if I do the matching at the scale V, I find that this lambda to the beta function of the low energy theory is equal to V times the original lambda 3n minus f, 3n minus f, and there's the power v to the 2f here, which is exactly right because we had f flavors that got vivs. So, I'm sorry, that's the other way around, right? It's 1 over v. 1 over v to the 2f. So it's the original theory being Higgsed by all the flavors getting vivs. So, okay, so this is the low energy scale. Now, in this low energy, what do we have? We just have the gauge bosons, but because it's supersymmetric, we also have the gauginos. So we have fermions. And what we saw that fermions do in our QCD, we have a fermion condensate. So it's very reasonable to assume that here too you're going to have gaugino condensation. So indeed, what's happening here is that there is a gaugino condensate here. What would be the typical, what would be the value of this gaugino condensate? So lambda should be the only thing that can show up is the strong coupling scale of the low energy theory. That is lambda L to the power 3, lambda L to the power 3, because we have, this is the fermion condensate. So now let's stick in the numbers. So now this lambda condensate is given by lambda L to the 3, and I can just read lambda L off from here. So it's lambda 3n minus f over v to the 2f to the power 1 over n minus f. And now remember, what is this v to the 2f? V to the 2f is exactly the determinant of m. So substituting this in, we have the determinant of m to the power 1 over n minus f. So we got exactly the superpotential that we had before. Now, remember, why is this connected to the superpotential? Because one of the terms that we had in the Lagrangian was this d squared theta w alpha, and the lowest component in w alpha was lambda alpha. So what this gives us in the Lagrangian is, or what this gives us, if I associate this with a superpotential, the thing that shows up here is lambda alpha. So you can say, you can view this in two ways. You can say that starting from the ADS superpotential that we derived, starting from this guess, we go along some flat direction, and we see that it corresponds to gaugino condensation in the remaining unbroken gauge group that we have. And notice also that this remaining gauge theory that we have can be very weakly coupled, because we're going along some flat direction V. The gauge bosons are getting mass that's proportional to V, and for large V, we get a theory that's weakly coupled, and we can trust calculations in this theory. Another way that you can view this is sort of in reverse. You can say, suppose I don't know anything about gaugino condensation. I can start with the ADS potential that I wrote before, and derive the fact that in this low energy theory, there is a Gaugian condensation, and this Gaugian condensation is something that we compute, and this is the value that we got for it. It's the low energy scale cubed, which is of course the only natural guess, the only possible guess, but we can think of this as a way to actually derive this Gaugian condensation. Yes?
Can you repeat how can I find the low energy scale? Sorry.
Yes, sure. So that's something that we previewed yesterday because it's gonna come up many, many times. So we said the following thing. We said that, let's do this again generally. Suppose that I have some theory up here and some theory down here that I'm gonna label with H and L. And this is some mass threshold. For example, it could be a scale M where some things get mass. Like maybe some of my fermions and scalars are gonna get mass there. But it could also be a scale where the gauge bosons get mass, which is the case here. So in this case, we have a Higgsing of the original gauge symmetry, and what's happening is that a lot of the gauge bosons are getting mass, and also some of the chiral fields are getting mass from this superpotential, and because they're eaten by the gauge bosons, by the usual Higgs mechanism. So what we're saying is the following. Up here we have some coupling GH, which is scale dependent, and down here we have a coupling GL, which is scale dependent. And what I want to do is I want to set them equal. I want to say that GH at M is equal to GL at M. And then I invert this and instead work in terms of lambda, and what I'll find is that so remember that what I want to use now is the fact that the easiest way to do this is just to say that lambda to the b to the e 8 pi squared over g squared is just, sorry, if I calculate this, it's mu, and here I have mu to the b, then this is a constant, and that's the thing that I'm calling lambda to the b. Okay, so now just do this at the scale m, and you find that lambda low b low equals m bl minus bh times lambda high bh.
Okay, but how the VEV is appeared?
Oh, the VEV is just the scale. So this is the scale where things get mass. Okay, this is the only scale appearing here. I took all the VEVs to be the same in this case. So everything is getting mass.
So this 2f is 3 times n minus f minus 3n minus f.
That's right, yeah. There's two ways you could look in this. You could look at this. One is just to say the power that appears here, it's just the difference between the two beta functions, and that's what you're doing. But you can also say how many flavors are getting mass, or how many flavors are getting VEVs, and that would be the right number. More questions? Okay, good. So, so that's very nice. We understand where this potential, where the superpotential is coming from. It's coming from Gaugian condensation in the unbroken gauge group. But when, but you could be very unhappy at this point because you'd say the following thing: look at this superpotential. What it wants to do is to push all the VEVs away from the origin. So let's look at the potential to see that a little more clearly. So remember, what is the scalar potential? The scalar potential, what I should do there is I should take dw over all the fields and square that, and similarly for the Q bars and so on. Now, this is a little tricky because it's a strongly coupled theory. Near the origin, I told you the first question we want to understand is whether we should be working with what are the degrees of freedom? Should we be working with the original quarks, or maybe in terms of the mesons? But let's suppose that we're going along one of these vevs, and let's suppose that the quarks are getting vevs which are quite large, and then our theory is weakly coupled, and then we can sensibly work with the original quarks. So roughly speaking, let's again take some choice of vevs and say that this is v1 squared to vx squared. And now let's look at what the potential does. So we have to take dw over dv1 squared, for example, and square that, and similarly for the other guys. And you see that what W roughly looks like is it looks like v1 squared to vf squared to the power minus 1 over n minus f. So when I take the derivative, I'm going to get some negative power of v. So the potential here goes to 0 as v goes to, the potential goes as some negative power of v. So very roughly speaking, what it does is the following. If I look at the potential as a function of v, where I should be imagining all the vevs, then it blows up at the origin, and it does something like this. So what does the theory want to do in this case? Well, it doesn't do anything sensible. There is no vacuum at any point, at any finite point in field space. So when we have a situation like this, we say that we have a runaway direction or runaway behavior or something like this. We don't have any minimum at any finite point. So what we've really seen is that if we take supersymmetric SUN with F flavors smaller than n, then there's really no ground state. There's no sensible ground state. So should we throw out this thing completely? No. One thing that we can do in order to make this sensible is essentially, what do we want to do? We want to add something that would make the potential rise, such that we will find a minimum somewhere at some finite point in field space. Another way to say this is that at this point, this theory has no moduli space. Right? There's no point in field space for which the potential vanishes. So there's no moduli space. So we want something that will make the potential rise at infinity. And so the obvious thing that you can do is you can add mass terms. So I can add the mass terms for all the flavors. That is, I want to add a piece to the superpotential, which is something that I'm adding at tree level, something classical that I'm adding at tree level, which is just sum over mi. Let me just call it this thing, MIA times the meson IA, or written in terms of the original fields, this is QI dot Q bar A. And we want to take this mass matrix here to have rank F, such that all the flavors are getting masses. When we do that, indeed the potential classically, you can see becomes, starts rising at infinity, because if you look at the W over, if I look at the W over dqi, for example, it gives me MIA Q bar A. And so when we look at the potential and square that, we're going to have this rise in the potential. It's not completely clear a priori that the minimum that we'll get is supersymmetric. I mean, in principle, we could either find a solution where the potential vanishes, all the F terms vanish, and then we have a supersymmetric minimum, or we could even have a supersymmetry breaking minimum. But in this case, we will find a supersymmetric minimum. So let's do that, and I'll actually leave the details of the exercise for you to do. So our full superpotential now is lambda to the 3n minus f over the determinant of n to this power plus mm written in matrix form. And now I can look at all the different f terms. So the f term for m is dw over dm. And I want to set that to 0. And when you do that, you can find that there is a solution, and the solution for the Mazon is this. It's lambda to the 3n minus f, the determinant of m to the power 1 over n times m to the minus 1. So this is the solution. And this gives us the location of the supersymmetric ground state. So the supersymmetric ground state is going to lie somewhere around here, and the value of m depends on the mass that we put in.
Sorry.
Yes?
My question concerns the numerical coefficient in front of the first term. Was the Gaussian condensation approved that will be faster?
So at this point, I'm not thinking about, let's forget about Gaussian condensation for now. Just take this as is. Okay, that's our result for the superpotential that's generated by non-perturbative effect.
Okay, but this would be 0 as well, you said.
No, it's not 0. This is the full superpotential. Okay, and now I'm looking for a minimum. Should be made before. Okay.
You said that in principle we can have some coefficient from this determinant. Right?
Yes, I said.
This coefficient in principle could be 0 or not.
Right, exactly.
So why you are considering non-zero?
Okay, so I didn't calculate that coefficient, but I gave you some argument that shows that there should be some non-zero coefficient, that this contribution should be there. And the thing that we argued was precisely this Gaussian condensation thing that we said. We said, look, if we have this superpotential that's generated with some non-zero coefficient, then it's consistent with having Gaussian condensation in the low energy theory.
Is that a proof that you have this?
No, it's not a proof, it's a conjecture. But now we'll see something that's closer to a proof.
Oh.
Yes. So you can say that's a very important point to make, is that a lot of the things that we say here are originally a conjecture, and then the question is, can you actually prove it? And one of the things that we're going to see now is actually the most, probably the most solid piece of evidence for actually having this. More questions? Okay, so let's look at something else which we can do with this superpotential. So again, this is the thing that we have from non-perturbative effect, and you'll see that there is one case where it becomes simple or particularly simple, and that's the case where n minus f equals 1. Then this power is just 1. So let's look at this case in particular. So now let's look at the special case of f equals n minus 1. So when f equals n minus 1, there are two things that happen. First of all, our superpotential becomes 2n plus 1 divided by the determinant of m. We don't have any fractional power. And the other thing that's happening is that as we move away from the origin, which is, we just said this is what's happening here, our low energy, the unbroken group in this case, is just nothing. This thing is just 1, so the gauge group is completely broken. And if we consider large vevs, then we have something that's very weakly coupled, and in principle we can do computations there. So then we can look at this superpotential and ask what could possibly generate a superpotential like this. So remember what the superpotential implies for the Lagrangian. So now I want to see what sorts of things does this generate at the level of the Lagrangian. So what am I supposed to do for the Lagrangian? One of the things that I will have in the Lagrangian is I'm supposed to take the second derivative of w with respect, for example, to dqi and dq bar j. And this will multiply the fermion qi and the fermion of qj. That's one of the contributions that is coming from this superpotential. So now, what is this thing? We have to take two derivatives of this superpotential. Here I have essentially q1 to qf, q1 bar to qf bar. So what this thing is going to give me is going to give me lambda to the 2n plus 1 divided by the determinant of qq bar, and then some extra powers, q1, 1 over q1 and 1 over q1 bar, for example, times psi, or let me keep this I and this guy j. And just to make things very clear, at this point when we're calculating the Lagrangian, I should substitute here the scalars. I should just be keeping the lowest order components of any chiral superfield, so these are really the scalars. So I'm putting these tildes here to make it absolutely clear that these are the scalars. Now I can expand, so I didn't finish writing this thing. So I have psi qi and psi q bar j. And now if I expand this thing, I can take, for example, I can write qi tilde is v plus some fluctuation qi tilde, and I will get a term in the potential that has a bunch of terms. The first one is one where I substitute v's for all the scalar fields, And then you see that I'm going to just be left with these guys. So this is going to be a mass term for the fermions. So the first thing I get is a mass term for the fermions. But I can also keep more powers of the scalars. I can keep more powers of these fluctuations here. And then I have some very higher dimension term that's generated. And it basically has, I can write it as psi qi, psi q bar j, and then lots of these scalars here. q1 tilde, q bar tilde 1, and then similar factors for each one of the flavors that appear here, up to f. So, written in terms of, let me show this diagrammatically. The thing that we're getting here is some sort of interaction that involves two fermion legs, let's say psi q1 and psi q1 bar, and then we have lots of scalar legs. So we have, first of all, q1 tilde, q1 bar tilde, all the way up to qf tilde, q bar f tilde, and then two more, q1 tilde, q1 bar tilde. So then the question is, what could possibly generate a contact term like this, or a higher dimension interaction like this? So this starts to look very, very close to the instanton amplitude that we talked about, that has one external leg for each one of the fermions that appear in the theory. So let's look at that. And now this is going to be pretty tricky to draw, but I'll do my best. So let's recall the instanton generated amplitude. That's something that is proportional to lambda to the b, which in this case is 2n plus 1. And it has one external leg for each fermion zero mode that appears. In our case, what are the fermions that appear? There is one fermion for each one of the q's. So there is psi q1 bar, psi qf to psi q bar f. But then there's also the contribution of the gauginos. And how many gauginos should we include? The contribution of the gauginos, the gauginos contribute to the anomaly as 2n. So altogether, we should include 2n gaugino legs. Now, this is not something that, if you haven't thought about instantons before, and if you haven't thought about the calculation of these anomalies, this is not something that you would wake up in the morning and realize, but let's just take it as a fact for now. And this is something that would take some reading and some work in order to convince yourself that that's really the case. But let's just take this as a fact for now. So then, what would the instanton amplitude look like? So I need to draw something like this. Let me do it the following way. So first of all, I have psi q1 and one gaugino leg lambda, and then I have psi q2 and a gaugino lambda, and so on and so forth until we get to psi qf, and let's see if that's the way, psi q n minus 1, and a gaugino lambda. So this includes all the fermion flavors and almost all the gauginos except for two remaining gaugino lines, lambda and lambda. But now remember, we have an interaction in the supersymmetric theory. We have an interaction that connects a gaugino, a scalar q, and the fermion psi q. So now we can use this interaction to sort of connect these legs. So I want to connect these legs and attach the scalar q1 over here. So this is the scalar q1. Similarly here, I can attach the scalar q2, and so on and so forth. Let's finish with psi q bar here. So connecting these two legs together, we're going to have q bar n minus 1. And finally, we have these two gaugino legs sticking out, so I'm going to do exactly the same thing. I'm going to attach, say, a q1 line here, and then this is a psi q1, and similarly here, I can attach a q1 bar, and then this is psi q1 bar, and I can stick in the vivs of these guys. So this is now a viv, and this is now a viv. So it's a big mess, but what we got in this case is precisely this thing that we had over here. We have an amplitude that's generated. We have a contribution to an amplitude that has all the scalars appear and two of the fermions. And it's proportional, because it's coming from this instanton that we had originally, it's proportional to lambda to the 2n plus 1. And all the other factors that appear are these expectation values v. And if you stick them all in, you'll see that you get exactly the right thing. So what have we seen? We have seen that for this special case of f equals to n minus 1, the instanton generates this ADS superpotential that we saw. Okay? So, coming back to the question that was asked here, this is a case where we have pretty solid proof that this superpotential is actually generated. Because remember, this is a theory that's completely Higgsed, it's weakly coupled. You can do an instanton calculation there, and you can trust the calculation, and you verify that you get exactly the right thing. And in particular, you can also, for this case, you can also calculate the prefactor. So for this lambda to the b over that q bar, in this case we can calculate the prefactor. And then all the prefactors in the other cases, we can relate to this one based on matching. Okay? So that's what happens in this case. Any questions? Okay, no questions. Okay, so let me summarize what we've seen here. I'm okay. I was getting worried about the time suddenly. Okay, so let me summarize what we've seen here. So we've looked at number of flavors smaller than n, and we saw a number of things. We saw that holomorphy plus symmetries determine WADS, which is the exact superpotential. And with the superpotential, what do we see that's happening? We see that we can describe the theory in terms of the mesons of the theory, that is the gauge invariants. And we see also that we're never at the origin. I mean, the theory is always away from the origin, meaning that the global symmetry that we started from, this SUF times SUF times U1B times U1R, but in particular this SUF, so this is the theory, this is the symmetry that we started from, but because we go away from the origin, we see that this guy is actually broken. So what we have here is something that's very similar to QCD in the sense that the theory confines. We have confinement and chiral symmetry breaking. Right? So the meson develops a wave, and so this SUF left times SUF right symmetry is broken. So from the point of view of exploring what possible things can a gauge theory do, so far we didn't get anything that was too striking, because this thing just does what, roughly speaking, what QCD does. Now, the nice thing from this is that we could actually calculate everything. We could calculate the waves, we could calculate the interactions in the low energy theory, because we have the exact superpotential that we wrote down. And if we wanted to think about, and as I said, one way we can think of this is to also, as a way to derive the instanton contribution, to derive the result for gaugino condensation. But you could say, you know, so far we saw something that's very similar to QCD. Can there be other things that we can establish? Do we have theories, for example, that confine and don't exhibit chiral symmetry breaking? Or maybe we have theories that don't confine at all in the infrared. So these are the things that we're going to see next. Okay, so the thing I'm going to do, as I said, is I'm going to skip one case and go directly to n+1 flavors, just because we don't have a lot of time. So let's now talk about f equals n+1. Okay. So the first thing we need to talk about, just like before, we need to ask what is the classical moduli space. Remember, we didn't add any superpotential. So the question is, when we look at the only part of the potential is coming from the d terms, so we want to ask, where is this thing? 0. That is, where do all the d terms vanish? Now, you can show, and actually 2 good references for this are the original papers actually by Affleck, Dine, and Seiberg, but also the book by Dine on SUSY and supergravity. And you might also want to check the book by Turning, which is called Modern Supersymmetry, and any number of other references. This is a very old subject. So anyway, the solutions, the moduli space here, the classical moduli space that solves this is the following. You can take Q to be V1 to Vn and 0 here, and you can take Qt, Q bar transposed to be some V1 bar, V bar in, and again 0 here, and V1 squared minus Vi squared minus V bar I squared is constant. So that's in terms of the original fields. You can show that, using an SUN and SUF transformations, you can diagonalize Q and bring it to this form, and then the form of Q bar is fixed like this. Now it's much easier to, we can go through this exercise, but we already said that we can always parameterize the d-flat directions using the gauge invariants. So instead of thinking about the Q's, I can just parameterize the flat directions using the gauge invariants. So what are the gauge invariants in this case? So the first gauge invariant that we can make is just like the thing that we had before, Qi dot Q bar A. And that's the Mazon, just like the Mazon that we have before. But there is another sort of invariant that we can have now, which is a baryon. So I can take Q1, let me actually write it this way. I can take Qi1 to Qin. They carry SUN indices that I can call, let me call them M1 to Mn. And I can, of course, contract them with an epsilon tensor. So there is an epsilon M1 to Mn here. And that's something that's invariant under the SUN, right? I can make SUN invariants either with a delta function or with an epsilon. And so this is something that I can do now because the number of flavors is bigger than the number of colors. So this is something that we can call the baryon because it's very similar to our known baryon. And let me denote it by, let me also anti-symmetrize over those indices. So I have epsilon I1 to In, and let me call this guy Bi. So it's basically the anti-symmetric product of NQs. And similarly, we also can make the same thing with the Q bars. So this guy looks like Q bar to the N with an index A. Now, if I count the number of baryons and mesons that I have, there are too many of them. I mean, they cannot possibly describe the original moduli space, so they satisfy some constraints. They're not all independent. So the constraints are the following. First of all, that M has to be equal to BI MIA B bar A. And also we have BI MIA equals 0 and B bar A MIA equals 0. So this is something that you can verify classically by either sticking in these values or any other way. For example, you'll see that these equations tell you that the rank of M is at most n. And that makes sense because this M is constructed by Q dot Q bar, so there's no way it can have rank larger than n. Okay, so this is the classical moduli space, but now we're interested in the quantum theory. So the question is, what happens to this classical moduli space? Remember in the example that we saw before, there was a classical moduli space and it just disappeared. I mean, it just didn't remain once we included the quantum corrections. Okay, so now we're asking about, can there be any superpotential that's generated in the quantum theory? Okay, so let's do the same exercise that we did before. We want something that's invariant under all the symmetries. So first of all, we have the SUF times SUF symmetry. And there are a number of invariants that we can make under that. The first is the determinant of M, just like we had before. And the second is I can write B bar A, MIA, BI. That's also an invariant. Okay, and you see that exactly because I'm just contracting the SUF cross SUF indices. So these are the these are the two invariants that I can write down. It also means that if so another thing that I want to check is U1 baryon number, and you see that both of these guys are invariant under that. And then there's another thing that we want to check, which is the R symmetry. So let's look at the R symmetry. For the R symmetry, you can convince yourself that det M has charge 2, and also B bar M B has charge 2. So this is exactly what we had before. Remember that the Q, for example, Q and Q bar had charges F minus N over F, and if I'm sorry, F over, was it over N or over F? Suddenly I can't remember. Over F, yes. So, and the other thing that's important here, of course, is that F equals N plus 1, so this is just 1 over F. So you can see that the determinant of M has charge 2, and so does this combination. And at this point, we can write down the following superpotential. So we know that that M should appear linearly if it appears, and this guy should also appear linearly. So in principle, I could write it like this. I could write that M minus, or actually, I want to write it the other way around. I can write B bar M B minus the determinant of M. But of course, I don't know this relative factor ahead of time. And in principle, there can be any function here of det m divided by b bar m b. And just to get the correct units, W has to have dimension 3. So this needs a lambda to the 2n plus 1 here. So again, you see that if I fix lambda here on dimensional grounds, and it appears as lambda to the b, because the beta function in this case, Rb, is 3n minus n plus 1, so that's 2n minus 1, and that corrects my, sorry, did I do this correctly? Yeah, that corrects this factor here. Okay. Now, in principle, as I said, I can have some arbitrary function here of these two guys, but what we can do is we can consider the classical limit of this. In the classical limit, what we would expect to get from the f terms, I can look at the equations of motion for all the fields. In this case, it's just the f term equations, and the thing that I would expect to recover are the classical constraints. So that fixes this function to be 1. So this function is really not there. It's equal to 1. And we can check this very easily. So for example, if I look at the B bar A equation, I should set dW over D bar A to 0, and that just tells me that MB is 0, and that's precisely the classical constraint that we had. And we can do this thing for the others too, and recover correctly all the classical constraints. Okay, so at this point, I can get rid of this function, and I have the exact superpotential in this case. So this is the exact superpotential. And the thing that's interesting about this is that it contains positive powers of the fields. So it doesn't push me away from the origin. I can have a minimum at the origin. I can also have lots of other supersymmetric minima at finite waves of these fields, but there is a SUSY minimum at m equals b bar equals 0, if we trust this superpotential. So that would suggest that perhaps there is no chiral symmetry breaking. Our full original symmetry is preserved. That's, of course, assuming that this is really the correct description, and we can describe the theory in terms of the mesons and the baryons, which is not an obvious thing, right? So if this is true, it seems that if we can describe the theory in terms of the mesons and the baryons, we would have an example where we have confinement. That is, the theory is properly described in terms of the mesons and the baryons, and there's no chiral symmetry breaking. So that's a very interesting possibility, one that we don't know in our real world, but it's something that we still need to check. So how do we check this? So there is one very non-trivial consistency check on this sort of thing. And let's describe that now. So the consistency check is something called a 't anomaly matching. And I'll just describe how we do this in this case, and then you can see how it works. So what's the thing that we're actually trying to check here? We have some UV theory that we know. This was our SUN theory with F flavors. And we want to know what is the low energy theory, what's down here. And we have some guess. We have some guess for the degrees of freedom here, in particular the fermions that appear here. Now, when we have fermions, they can generate anomalies. They can contribute to all sorts of anomalies. And so basically what this is going to allow us to do is to check whether the low energy theory, in particular the fermion content of the low energy theory, is consistent with what we have up here. So let's do it, and then we'll see how that happens. Now, the thing that it relies on is having some unbroken global symmetry. You can only do this, you can only apply this if you have a global symmetry that's unbroken. So the thing we do is the following. Let's first of all talk about our UV theory, the original theory. It had a very large global symmetry group. And now the thing that we want to see is, we want to say the following. Suppose, let me call this thing G. So suppose G is unbroken in the low energy theory. So this just stands for the low energy theory. Now I can take this global symmetry that I had originally and try to gauge it. Try to just gauge this full global symmetry by some weak and associated weak coupling with it. Now, in this case, I can't do that. And why can't I do that? Because there are all sorts of anomalies that appear here. I know the original theory, and I can calculate the contribution to various anomalies. So there is an SUF cubed anomaly. I'm talking about the high energy theory or the UV theory. There's an F cubed anomaly. There's an SUF left squared times U1B. There's U1B cubed, and a whole host of other anomalies. So I can say, okay, let's do the following. Let's add SUN singlets that transform under G, under this global symmetry. I'm going to call them SN. There is a bunch of singlets, such that now G is anomaly free. And so with the addition of these SNs, I can gauge this global symmetry. So I'll have my original quarks and also these SNs in the original theory. So now let's look, for example, at SUF left cubed. Let's look at this anomaly. The original fields that I had were Q's and Q bars. I don't care about the Q bars, right? Because they don't transform under this SUF left. So I just need to include the contribution of the Q's. And what are the Q's? The Q's are fundamentals of SUF left, and how many fundamentals do I have? The Q carries SUN index 2, so I have n fundamentals of SUF left. So the contributions of the Q to the anomaly is the contribution of n fundamentals. And the contributions of the SNs will have to precisely cancel that. For example, I can take some of the SNs to be n anti-fundamentals of SUF. And maybe I'll need to add other things. Now let's look at the low energy theory. Now we look at the low energy theory. So remember we started with the Q's and Q bars, and we also had these SN here, these SNs here. Now something, as we go to low energy, something is happening to the SUN, but nothing is happening to these guys, because I'm assuming that I gauged the G group very, very weakly, so nothing interesting is happening. And here, basically, I don't know what's going on. So I don't know which fermions appear here. But now we're saying exactly the thing that we said. First of all, we assume that G is unbroken. And we have a guess for the fields here. Our guess for the fields here are the mesons and the baryons. And let's see if this works out. So now I can do the following thing. I can calculate the contribution of the mesons and baryons to the anomalies, of G. Now, I know that the low energy theory needs to remain, must remain anomaly free, because I gauged this symmetry. So I know that these anomalies here must be equal to the contribution of the SNs to the anomaly. And this contribution was exactly the opposite of the contribution of the Q and Q bar to the anomaly. So what we get is the following consistency check. We see that the various contributions to the anomaly that we have in the low energy theory must match exactly the contributions to the anomaly that we had in the original theory. And that's this Tooft anomaly matching. So we see that the contributions of M, B, B bar to the G anomalies must be equal to the contribution of Q bar. So let's look at this SUF left cubed anomaly that we started from. So we said that the Q's are n fundamentals of that. Now what do we have in the low energy theory? Now we have the mesons. Let's put indices on them, IA. And remember that our SUF L index is I. And we have the BI, and we have the B bar A. Now if I'm a little careful, then this I and A needs to be up here. This guy doesn't see the SUF left. And what are these guys? Here I have the index A, which runs from 1 to F. So I have F fundamentals of SUF left. And remember, F is equal to n plus 1. And these guys are now I just have one of these guys, and it's an anti-fundamental of, and it's one anti-fundamental of SUF left. So altogether, adding these two guys together, I'm left with F minus 1, that is n fundamentals of SUF left. And you see that that's exactly the same number as the number of fundamentals that we had contributing in the UV theory. Okay, so what does it tell us? It tells us that as far as the SUF left is concerned, the contribution of the mesons and baryons in the low energy theory is consistent. Now we can go through the whole list. There is a big list of anomalies here. You can calculate them all, and you can verify that everything works out. So that's a very strong consistency check. It's a very non-trivial check, and it tells you that this description is probably consistent. That is, what have we learned from this? We are now fairly certain that the IR theory is described by the mesons and baryons with the superpotential that we wrote down before. And in particular, the thing that we learned is that the origin is okay. That is, it's a supersymmetric ground state. It's part of the Modulite space. And that means that we have an example of confinement without chiral symmetry breaking. And you see that it's very, very non-trivial. I mean, we have a full description, we have the full superpotential for this theory, and so we can calculate lots of things. Certainly the spectra of light modes at each point, and that's a very interesting example. So let's see how much time we have. Okay, we have 10 minutes. So let me think about what do I want to leave out. Okay, so here's an example that I was going to do, and I'm not going to do that because we don't have a lot of time. But it shouldn't be that hard to work out. And that's something that would give us extra confidence in what we're doing. Okay, I should say that this result is due to Seiberg, and everything that I'm going to say from now on is really due to Seiberg from 94 and 95. And besides the references that I gave you before, there are the original papers, which are very, very nice once you have some background and understand what's going on. And there's also nice, very nice lecture notes by Intriligator and Seiberg. There's actually two sets of lecture notes, ones that are from roughly 95 or 96, and then another one that's about 10 years later. Okay, so the example that I was going to do explicitly, but I'm not, is the following. So we can take this f equals n plus 1 case, and we can add masses for two flavors. And when these flavors become heavy, we should go from this case to n equals n minus 1. And this is something that we already worked out. So if everything is working as it should be, then we should recover the results that we had before. And that's a very nice check on the theory. And remember, this case is the case where we can actually compare to the instanton calculation. So we have a lot of confidence in what's going on. And so that's a very strong check on this story. So let me just outline how this thing is going to go. So we're going to add a term to the superpotential, which is some mass n times qn dot q bar n plus some mass that I'm going to call f qf dot q bar f. And now I know that I should write this thing as m and n because the theory confines, and mff. So I can describe it in terms of the mesons. And now it's a pretty simple exercise. What you should do is you should take the full superpotential, which is this thing that we wrote here, plus this delta W. And we're getting rid of the two last flavors, and that means that we're getting rid of all the baryons, because we're not going to be able to make baryons anymore, because the number of flavors that we have is smaller than the number of colors. And so I should look at the equations of motion for m and a for all a's. So now my a underline runs from 1 to n minus 1 only. And let me erase this. And similarly, m a n and all the bi's and all the b bar a's. So for each one of them, I should set, for example, the f term of m and a to 0. For each one of them, I should look at the f term and take the derivative of the potential of the superpotential and set it to 0, and then substitute back into the superpotential. And once you do that, you're going to find the ADS superpotential that we wrote before. That is, you're going to find lambda n to the correct power here, divided by det m prime, where these are just the remaining mesons in this case. So I can take my full meson matrix and write it as some m prime, and then m n n, m f f. Let's diagonalize it so everything else is 0. And the thing that will remain is just the determinant of this guy. And it's not very hard to do. So it's something that you can do. And because you're going to recover this ADS superpotential, that gives you a lot of confidence that this thing is actually there and is actually generated. Okay, very good. Now, of course, you can say, why omit the f equals n? So that's absolutely something that you could do. You could just give mass to one flavor and see what's going on for f equals n. And that's also a very interesting example, but we really don't have time for that. Okay, so let's see. So I'm almost done. I have 5 minutes in which to cover Seiberg duality. So I'm not going to do that, but maybe I'll say a few words about it. But even before that, I want to say something that I think is important to say about this story, just to complete it. Okay, so we wrote down this, let me clear the mess here. We have this nice superpotential that we wrote down, and we know it exactly. But remember that, but now it's important to know what we know and what we don't know, right? That's really always the most important thing, is to also understand what you don't know. So remember that in order to find the Lagrangian, you need two things. You need W, but you also need the Scalar potential. And the Scalar potential is something that's a real field. It depends on all the phi's and all the phi daggers. It's not chiral. So all these nice arguments that I had that relied on holomorphy cannot be applied here. And it's important to remember how powerful all these, how powerful holomorphy was really in this whole story. Because when I said, we look for something that's invariant under SUF times SUF, and so on and so forth, the only things that I had to play with for the smaller number of flavors, for example, was M. But I didn't have M dagger, right? If I have M dagger too, then no problem. I can write anything that involves M dagger to whatever power I want, and that's going to be completely invariant. But it really mattered that we could only write down things with the Mazon and not the Mazon dagger. But that's no longer the case for the Scalar potential. So what can we say about the Scalar potential? So the first thing that we're saying here is that we gave some very strong arguments for why this theory is really described at low energies by the mesons and the baryons. And of course, if that's to make sense, what it means is that my Scalar potential should start as something that's canonically normalized in the mesons and the baryons. But then, of course, there could be all sorts of other corrections, and these corrections are things that I don't know in general. So let's just talk about the mesons, for example, and in this case, what is the Scalar potential? So the first thing that we have is the trace of M dagger M over lambda squared. So what did I do here? I wrote down something that's invariant under the SUF times SUF, and give me something that's canonically normalized. If I start to write down the different M's here, then it's really just going to start like MIA dagger MIA. And I also stuck in the lambda squared here because M has dimension 2, and I want to make it canonically normalized. So this is the first term that I have, and this coefficient better be 1. In other words, if it's not 1, then I should rescale my M's by some constant. But once we go through this exercise, for example, of going down to n-1 flavors, and we derive the instanton contribution, and we compare it to the actual contribution, then we can be certain about this prefactor here. But then there's all sorts of other terms, like I can write trace M dagger M dagger M divided by lambda to the 4, and all sorts of other higher order terms, and these coefficients are things that I don't know. So it's not like I know the full theory. There are some things that I know about the theory. You see that near the origin, I pretty much know everything because all these, because when I start expanding these things, it's just going to give me, it's not going to give me anything. But as we go to higher energies, or as we go away from the origin, there's a lot that we don't know. Okay? So all the uncertainty is here in the Scalar potential. And the same story applies for everything else that we said before. Okay, so let me also tell you what I'm not going to tell you just in one line, and then we'll conclude. So I'll just steal 2 minutes. So the next thing I was hoping to do, I guess unrealistically, is to be able to cover Seiberg duality. And the story here is that you basically look again at SUN with now F flavors that are bigger than or equal to n plus 2. And a lot of it is very similar. I mean, still we can write down the mesons, we can write down the baryons, only they carry more indices now. There are more baryons of each type. There's a bunch of classical constraints that you write down. And then the question is, what is the moduli space of the quantum theory? And the first thing that you can do in this case is you can look at 't anomaly matching, just like we did before. You can ask, is it consistent to have the origin in the moduli space? Is it possible that the theory has a ground state at the origin, such that the original symmetry, same symmetry that we have been writing all the time, is it possible that this symmetry is unbroken? And you look at the 't anomaly matching conditions and they don't work. So you know that if the theory lives at the origin, then the mesons and the baryons don't give you a correct description. Okay, so at this point you don't know what to do. But Seiberg found a really interesting solution that does match all these conditions. And remember, there are many conditions and they're very non-trivial. And the solution that he found was in terms of a completely different gauge theory. So what is this other solution? This other solution is in terms of an SU F minus N gauge theory. So a completely different gauge theory, a completely different set of gauge bosons, and still F flavors that are exactly the same sort of flavors that I had before, with very similar transformations under these under the global symmetry group, plus F squared singlets of the SU F minus N. And these singlets, let's call them M tilde IA. So they look very similar to these mesons that we have over here. So the claim is, if you go through this anomaly matching, you see that these guys satisfy all the 't anomaly matching conditions. And then you can conclude that this gives an alternative description of the theory at the origin. Now, there's one more piece to the story. If I took these two theories and let them flow to the infrared, they wouldn't do the same thing. But there's another thing that we have to add over here, which is a superpotential. And the superpotential is of the form M tilde IA QI dot Q bar A, where these Q and Q bar are the quarks of the new theory. So this theory is usually referred to as the electric theory, and this is usually referred to as the magnetic theory. And the thing that's the interesting thing that happens is that you start from our electric theory and our magnetic theory in the UV, and you let them flow to the IR, and they both flow to the same infrared theory. Now, I'm not going to describe this. You can already see why this term is important. For one reason is that if you wanted to compare the moduli spaces of the two theories, then it seems like here you would have two mesons. You would have this M tilde guy, and you would also have the old meson M coming from this. But now that we write down the superpotential, this is a mass term, and it gets rid of this guy, for example, if I go along a flat direction associated with this. So anyway, this is the story. There are many, many interesting things to do with it, of course, but that's something that we won't have time to do. Okay, so we'll stop here. Questions?
This minus sign between the first term B square and B minus the term, is this coming from the demanding for SUSY vacuum?
This minus sign here is something that you can fix from the comparison to the classical constraints that we wrote down. So for example,
You look at our constraint B bar M equals to 0. So the first term is
right. But now let's look at the F term for M. Okay. So let me look at. So basically here. So let's suppose I'm looking at MIA, and I'm looking at the F term for that. So this guy over here is going to give me B bar A, BA, and this guy is going to give me the cofactor of MIA, and then that thing needs to vanish. But now I can take this thing and multiply it again by MIA, and I'll basically restore this MIA here and get the determinant of M here. And that's the other classical constraint that we had. Okay?
Okay, so this is before using the constraints. The superpotential are not allowed to talk about constraints.
Well, there's the classical story and there's the quantum story. Okay? I can look at the theory classically. Classically, you can derive these constraints easily in principle. I mean, it maybe takes a little bit of work, but you're just playing with numbers, right? Classically, M times B is just M times B. I'm just multiplying matrices. So I can work out the classical constraints, and you can convince yourself that you get the classical constraints that we said that we have. Then I'm writing down, then I'm going to the quantum theory, and I'm writing this superpotential. And the question is, then, these, I can look at the supersymmetric minimum, and I can see that the supersymmetric minimum respects all these classical constraints that we had. So it's logical to expect that the constraints could be modified by something, but the something should be small when you go along a flat direction and turn on a VEV that's very, very large compared to lambda, because then you get something that's weakly coupled, right? So at least for V, if I turn on VEVs that are much bigger than lambda, I should recover the classical constraints. And that's the thing that I'm seeing here. Now, in this particular case, the classical constraints are actually not modified at all. They just remain as they were. The case of f equals n that I skipped, this is a case where the classical constraint is modified. It's modified by something that is proportional to lambda to the b, lambda to the 2n. But again, if we turn on a VEV that's very, very large, we can neglect that. But for the important requirement, or the consistency check that you're looking for, is that for large VEVs will restore the classical behavior. More questions? Okay, so we're very overwhelmed, but it's life, right? Okay, so thank you very much.